Thank you. Yeah, I'm a lover of all sub-angstrom particles. As long as I can shine them onto the material and learn something, I'm happy. So today's talk is really about material synthesis. It's a hard problem. And we're using X-rays to try to solve parts of that problem. And I am coming from this little star in this blue square. We're about 20 miles away from the Wyoming border. And so here's our campus up against the Rocky Mountains, not quite in the Rocky Mountains. And yeah. So my group is really out to study materials discovery. It's a hard problem. And we really view this problem into three main challenges. And this is where we're focusing our efforts. We're interested in functional materials. So to make new functional materials, well, how do we selectively make and break bonds in the solid state? So I'm in a chemistry department, so I work with a lot of graduate students and undergraduate students who like to think about this, because this is the only synthesis that they really get exposed to in their early years of training. And so if you have some sort of organic molecule, and we can now know through various forms of nuclear magnetic resonance spectroscopy to deduce mechanisms of how we get from one species to another. And we're not quite there yet in solid-state synthesis, but that's where I want us to get. We're also interested in how structures can have dynamics that enable functional properties. And for this, we're spending some time looking at dynamics in hybrid perovskites. These materials are rather fascinating. They've captured our imagination for being able to make a 23% efficient solar cell using spray painting. I'm oversimplifying a little bit, but there are a lot of cool science questions that we can study. But overarching both of these main problems is how do we actually study these often disordered systems? And this is where I take advantage of our wonderful user facilities here or at various neutron facilities as well. So I wanted to give you a quick two-slide overview of our work on hybrid perovskites because I'd love to talk to any of you who have some really interesting solutions to some of our problems, one of which is this complex and functional dynamic disorder in hybrid perovskites. So when I was a student of material science and engineering as an undergraduate, I learned about these types of materials, things like silicon, gallium arsenide, or if you wanted to get really, really complicated, you can get into copper indium gallium sulfide selenides or copper zinc tin sulfides. But if I turn down the color on all of these, they would all look like silicon. They're all rigid tetrahedral networks. And so the physics aren't that different when I go from one material to another. Now, the details are drastically different, but we know more or less how to think about these types of materials. Now, when I think about a hybrid perovskite, they don't look like these. They look more like this material, potassium cyanide, which I don't think we're going to find in a solar cell, but it does have two industrially relevant applications that I'm aware of, one of which is gold mining, and the other is espionage, if you get caught. And so potassium cyanide is this really rich material where you have cyanide trying to approximate a sphere. At room temperature, it's dynamically disordered and forms a plastic crystal where there's no orientational order between the cyanide molecules, but there's translational order. And that's really what these materials look like, where you have this inorganic lattice, often composed of, let's say, lead and iodine, but then you have this A-site void where you're shoving in an organic molecule that tries to become a sphere. And so the point groups are, of course, incompatible, so it spins at room temperature. It's dynamically disordered and sits in one place for not longer than about 2 to 14 picoseconds. And so how do we think about a high-performance semiconductor where you have all of this disorder? And does it enable functional properties? And so in some of our work, we've looked at anharmonicity and different types of defect-ordered perovskites. And so in this paper, we actually took advantage of some X-ray pair distribution function data collected at 11IDB. And Eve is still with us. Annalise has actually moved on as a director's postdoctoral fellow at NREL. And Eve is still working on some of these systems. So these were data put together with neutron diffraction, but we've also used 11BM to characterize phase diagrams as we mix things like methyl ammonium and cesium to understand how you form orientational glasses. So I mentioned how these organic molecules spin around to try to approximate a sphere. Well, it turns out when you put in small amounts of cesium, you effectively freeze them. You inhibit their dynamics, and they behave glassy. So you observe thermodynamics that resembles that of a glass, even though you have this crystalline framework that you can use crystallography to study. So these fascinating materials, and the properties all follow these rich phase diagrams. And just to summarize, one little neat trick about this phase diagram is these materials can go cubic to tetragonal back to cubic, where they have these re-entrant phase diagrams, which are usually supportive of some sort of underlying entropy-driven transition, which I think are fascinating. But that's not today's talk. Today, I really want to talk about our efforts to try to understand how do you selectively make and break bonds in the solid state. And so here's the outline for today. I want to talk about kinetic control in materials chemistry. I want to provide you my definitions. Hopefully they're consistent with your definitions, but I just want to make sure that we're using the same words. Talk about some of our contributions in kinetic control in solid-state chemistry. We'll be talking a lot about metathesis reactions today, where we're reacting different metal salts to make functional materials. And we're going to follow these reactions in situ and try to figure out how we're getting around diffusion barriers in material synthesis. We've used this to make some metastable materials, whether or not it's different polymorphs of superconducting copper selenide or different yttrium manganese oxide compounds. And this work is done primarily by two graduate students. One is Andy Martinolich, who's now a Resnick postdoctoral fellow at Caltech, and then Paul Todd, who's in his 4th year. So here's a problem. I have two molecules, same chemical formula, but different structures. This is a problem in organic chemistry that was solved over 100 years ago. So I have isopropanol or 1-propanol. If I take propylene and heat it up with a little bit of water, this is what we get. It's the stable molecule. But you can go and potentially predict some metastable molecule, like 1-propanol. Well, organic chemists know how to make this molecule. You can take a Grignard reagent, basically an ethyl magnesium bromide, react it with formic acid, and voila, you can make this metastable compound. When I go to crystalline inorganic solids, that's not always the case. So if I have some, let's say, MX2 phase that's stable, and then something else that's metastable under ambient conditions, how do we make that? Sometimes we can apply some other thermodynamic parameter like pressure to stabilize it and then quench a reaction, but that's not always the case. And so given some prediction, how can we actually make a compound? So I was trained as a material science undergraduate, and so I'm not used to thinking about molecular structures, but rather phase equilibria. And so this is my view of organic chemistry, where if I have carbon, oxygen, and hydrogen, the ternary phase space at 0 Kelvin is rather limited. We get some methane, some water, some CO2. Now, we know that there are many other metastable compounds predicted, and this you can generate yourself from the materials project. I'm slightly plagiarizing the idea from Mercury Canetsidis and Dave Johnson, who I saw this present this when I was a student. But my point is that there are a lot of metastable compounds that could be out there. We're not seeing them. And so how do we increase the diversity of functional materials that are out there, especially if we're only ever making materials that are the true thermodynamic ground state for a particular mixture or a mixture of chemical potentials? So how do we make these? And there are a lot of reasons why you might want to do this. So operating in this framework of reaction by design, whether or not you're thinking about amorphous prenuclei or different molecular clusters and having them condense and crystallize, maybe that's a cool way to find new materials. I think you can get novel reactivity. So if you think about novel reaction pathways, well, you can actually get function out of reactivity. And this is how we can store energy. So whether or not you're thinking about peroxo-like species in lithium-ion batteries to get an extra few electrons out of your material. But we can also get remarkable emergent properties like superconductivity or high-temperature superconductivity. So if you take this iron selenide-based compound, it's a superconductor with a transition temperature of around 8 Kelvin. But if you do soft chemistry, so nice elegant, kinetically controlled reaction called a Birch reduction, which is actually used in organic chemistry, you can insert lithium along with some ligating ammonia or amide species, stuffs in between these layers, inserting an extra electron into the layer, and you get a transition temperature that's a factor of more than 4 higher. And so soft chemistry can actually give you remarkably new properties. And we live in what I consider to be a materials genome milieu. It's really a social setting where we have access to high throughput computations. And so density functional theory has really been a champion for predicting many different new functional materials, whether or not they're superconductors, transparent conductors, or battery materials. There's some great triumphs out there. And so can theory, or density functional theory, actually inform synthesis? I think yes. I think it can if we ask the right questions. So there's this nice paper from Gerard Seder's group looking at the formation of iron-sulfur polymorphs, whether or not it's pyrite or marcasite. And using some density functional theory along with classical nucleation theory, you can map out this effectively a phase diagram that looks at the activation barrier to making marcasite versus pyrite as a function of pH. And so at low pHs, you would expect to make marcasite, or at high pHs, you'd expect to get pyrite, which is really the true thermodynamic ground state. And this turns out to be what's observed in a lot of hydrothermal reactions. And so thinking about stability as a function of particle size or surface termination, we can plug this into simple theories to learn quite a bit. But it doesn't tell us all the answers. So we need complementary experiments. We need to observe what's actually going on in a reaction. That's not an easy problem. We need to see what's happening as it happens. And I still think there's a space for exploratory discovery of new crystal structures and compositions, things that we just don't even know about and will never come out of a machine learning algorithm, for instance. If you don't have it in your training basis set, you're never going to see it. So here's where we start our definition. So I apologize if this is a little too rudimentary, but I want to make sure we're speaking the same language. So when I think about most material synthesis reactions, I really think about them as some thermodynamically controlled, diffusion-limited process. Whereas if I think about how I teach this to first-year undergraduates, we have some reactants at a higher energy, and they have to end up at some stable product. The reaction runs downhill in energy space. And let's say there's some metastable product, call it a different polymorph if we want to. It's really the lattice energy that is driving formation of this product, in that it has a stronger lattice energy than the reactant, so it goes forward. And so our solid-state reactions are often diffusion-limited. We have some very high barrier with a KT that gives us temperatures of, let's say, 500 degrees Celsius to 1,000 degrees Celsius, depending on the material. And so we have to crank up the temperature to initiate and propagate this reaction, drive it all the way to completion. And even then still, it can get stuck. So usually in this kind of a setting, if the barrier is low enough to go from reactants to this metastable product, there's usually enough thermal energy to keep going all the way to the most stable polymorph in the system. So it's very hard to stop your reaction here. But we can kinetically trap reactions. So if we want to think about making diamond as opposed to graphite, you can apply some external potential, call it pressure or a dielectric environment like we use in hydrothermal or solvothermal reactions, where you reorganize the potential energy landscape. So if I apply 5 gigapascals of pressure, diamond becomes more stable than graphite. You can then turn on temperature. The reactants will fall into the thermodynamic ground state. You can then turn off temperature. It's stuck in that configuration, and then you eventually release the pressure. And then this is hopefully kinetically stable at ambient conditions. So you can study it. And this is something we know how to do. We don't necessarily know how to predict it in all cases, but this is manageable. That's not what I'm trying to talk about today. What I'm trying to talk about when I talk about kinetic control is this cartoon, where we're changing a barrier height. So if I have some reactant that can go to some stable product, I want to make this initial barrier very low, and someday I hope that we'll be able to actually make this barrier even higher, so that we can effectively have a reaction stop here along some reaction coordinate, some reaction progress. So I can do the chemistry at a fairly low temperature, and it will never convert to the next product. But that's a hard problem. How do we actually control barriers in a solid-state reaction at low temperature? I mean, solids are solid because they're solid. So we need to think about a way to to do this in a way where we're still working with solids, or at least provide an interface where things can be more mobile. So now we'll start talking about some of the things that we've been doing. So let's say I wanted to make FeS2, iron pyrite. It actually poses some challenges, even though it's a thermodynamically stable compound under ambient conditions. You can combine 1 part iron, 2 parts sulfur, make this. It's the primary electrode in energizers, batteries. It's been around for a while. There have been proposals of using it as a photovoltaic material. If we look at the phase diagram, if I mix 1 part iron, 2 parts sulfur, takes me right around here. I see pyrite FeS2, and it has a decomposition temperature of about 743 degrees Celsius. So I can't go hotter than that, otherwise it falls apart. So I also can't go that hot because sulfur is going to volatilize. So it's going to reach about 1 atmosphere at 400 degrees Celsius, so about 700 degrees Celsius is about as high as I would want to heat this up in a sealed container. So you can mix these together in a sealed ampule, heat them up, and wait. It might be done in a week, it might be done in 2 weeks. Don't really know, depends on how finely you've cut up your pieces of iron. It's a little bit tricky. So we took a different approach. And our approach was based off of a talk I saw from Rick Kainer when I was a graduate student on these types of reactions, where you can take something like molybdenum chloride, sodium sulfide, and you can heat them up just oh so gently. Let's call it 40 degrees Celsius. This spontaneously happens very rapidly with a large exothermic event. So here's a little snapshot of a video, which is done in about 0.8 seconds, 0.9 seconds, where you're seeing basically a flame and the vaporization of a bunch of sulfur as you make molybdenum sulfide and sodium sulfide. Now, if you try to make molybdenum sulfide from molybdenum and sulfur, it's not going to work very well. I often use molybdenum as a crucible material because it's rather inert. So what do I take away from this? So I love that this reaction is not really diffusion limited. When I think about this, it's not taking really any thermal energy to get this thing going. So from the cartoons I showed you, it has a really low initial activation barrier. But the thing that I don't love about it is that it self-heats up to about 1,300 degrees Celsius. So at the end of the day, the system has enough thermal energy to fall into whatever potential well it needs to. But then I got to thinking, well, how is this the case? How is this so reactive or labile? And you're taking two solid-state salts. They're initially reacting. They're producing molten sodium chloride, of course. But what does this process look like on a molecular scale? On one hand, we can think about ionic intermediates, where you're getting pseudo-topochemistry. Thinking about this, like kind of how like a lithium-ion battery might work, where you're kind of interdiffusing to make different non-stoichiometric intermediates. Or is it something completely on the other end of the spectrum, where you're getting stepwise reaction conversion to elemental intermediates? And these are just hypotheses, right? So this could go all the way to molybdenum 0 nanoparticles and sulfur 0 nanoparticles, which are then highly reactive because they have so much surface area, and that then they react. And I don't know what the answer is. But I think with modern X-ray science, we could probably actually study this, only 0.9 seconds. So for our first pass, we looked at a much more gentle reaction. So to make FeS2 through this metathesis reaction or double salt exchange, you can take iron dichloride and Na2S2, so sodium persulfide, which in the crystal structure actually has these preformed little dianionic units. This proceeds stoichiometrically to make iron S2 and sodium chloride. So the reaction proceeds under vacuum. After about 24 hours of heating at 350 degrees Celsius, it doesn't self-propagate, it doesn't self-heat, it doesn't explode. You get this really nice, clean product. Contrasts the previous conditions I mentioned, where you're reacting the elements at 700 degrees Celsius for a week or longer. But how does it work? What's the nature of the intermediates? And so we did this reaction to lower and subsequently higher temperatures, like 100 degrees, 150 degrees. We'd quench them from a furnace. Then we'd pack them up into a capillary, and then about 2 to 3 weeks later, we'd have our data from 11 BM. And we could see things like NaFeS2 and sulfur 8 as intermediates, which suggested that these anions were disproportionating and then comproportionating back together, but that left something to be desired because there's a lot of chemistry that can happen in the 2 to 3 weeks between the reaction happening, getting quenched, and then looking at it. So we had to change our procedure. So I was a student alongside Daniel Shoemaker, so of course I read his papers and decided to try some of these experiments where we can take our reactants, seal them in a capillary, and we can put the capillary into a glorified toaster oven or a furnace, apply a linear heating rate, bring in our X-rays, collect powder diffraction data, and get our nice one-dimensional pattern of powder diffraction. To this audience, I probably don't need to explain how to interpret a powder diffraction pattern, but if you're not used to it, we can basically just think about each peak as a part of a fingerprint of each crystalline phase. We do a little bit more than just fingerprinting. We do a full quantitative Rietveld analysis for each diffraction pattern that we collect. And we don't just collect one, but we'll collect a couple hundred to 1,000 diffraction patterns as we increase the temperature or dwell at a particular time as we watch the reaction unfold. So you can take a peak from, let's say, iron chloride and watch it eventually disappear as new phases come in. And so when we do this, particularly with the non-igniting metal chloride sodium sulfide reactions, we've looked at things like iron, cobalt, and nickel. They all look virtually the same, but I'm just going to focus on iron today. We see something that looks like a diffusion-limited reaction. So we're effectively going to go from reactants and hit a lot of phases on the phase diagram as we get to where it should stoichiometrically. And so walking through this color map, so we have reactants down here, we have products up here, and if you follow individual blue lines shown actually on a log scale, you can see different things happening in different zones. Plotted over here are actually differential scaling calorimetry data plotted on a different sample, admittedly, but you can see things actually correlating. So the first thing that happens is actually a little peak that grows in here, and that corresponds to the formation of sodium chloride. And in the calorimetry, we actually see a little tiny bump. So that's what I'm depicting here. We hop over one barrier into one potential well, and then we form several other phases. I'm skipping all of the details for this colloquium audience, but we form a bunch of sulfur-deficient metal sulfides and a bunch of sulfur-deficient sodium sulfides. And that just kind of hops along a cascade of reactions and eventually ends up with our products. To me, this is a fairly intuitive perspective, but it's telling us that it's this kind of pseudo-topic chemistry where you're just kind of pulling apart the reactants and starting to make intermediates that look kind of like the products from a composition perspective. And then we had a happy accident. So Andy, the student, was working on mixtures of these powders. When you mix them together and keep them in a glove box, they have these nice pastel colors associated with them. Well, one day he was taking the mortar and pestles out of the glove box to clean them, and there was some residual powder left on them. And you can't actually see it here because they're black. The powders just turn black just upon hitting air. And so where we live in Fort Collins, our ambient humidity is around 15%, which is pretty dry. If you've ever taken an anhydrous metal chloride out of a glove box or opened a brand new vial of it in air, it turns into soup. It's deliquescent. It picks up moisture from the air and turns into a slurry. Whereas these stayed dry. Also, if you've ever taken a sodium sulfide from an anhydrous condition into an environment, you will notice it immediately because it will release H2S, which we're very sensitive to. And so these didn't produce any odor. They were, of course, first taken into the fume hood before bringing them out. But we noticed some chemistry was happening at room temperature. So that gave us pause. So we thought, well, let's look at that. So when you take a look at a powder diffraction pattern of that black material, before it's been heated, you see sodium chloride. There are a couple of other little things in there, but we can ignore those for now. But it's effectively sodium chloride. No amount of iron or sulfur visible from powder diffraction. It's in there, but it's not a crystalline phase. So our sodium chloride's already formed. And then after heating to about 150 degrees Celsius, the iron pyrite crystallizes directly. I'll point out that this behavior is identical in nickel and cobalt, but completely different crystal structures for nickel. And so our pathway is different. So we have air exposure, so our barrier must be low, and then we have this nucleation-limited transformation to crystalline phases. But that left us wondering, well, what's this intermediate? It's not showing up in powder diffraction. So naturally, we turned to diffuse X-ray scattering and pair distribution function analysis, where instead of having Bragg features, we have very broad diffusive features that we couldn't actually see on the last slide. We can apply a numerical Fourier transform to extract the pair distribution function, whereas if we had a totally crystalline phase, we'd have nice correlations going out to virtually infinite angstroms, given enough reciprocal space resolution, or you can look at completely amorphous phases. And so in our material, we know for a fact that we have crystalline sodium chloride. And so at high R, we can actually model that sodium chloride very nicely. We can then subtract that off of our data, and we're left behind with a couple of pair correlations at very short distances, corresponding to some sort of amorphous phase. And so you can take the crystal structures of pyrite or this metastable form of FeSe, referred to as the mineral machinoite. You can calculate what a kind of a 10 angstrom particle should look like. And actually, this phase does a pretty good job of modeling this difference curve. And so I wasn't quite happy with that. So Andy went into the ICSD, the Inorganic Crystal Structure Database, and pulled out a large number of iron-oxygen compounds and when octahedral or tetrahedral or square pyramidal coordination geometries and plotted where their bond distances should be. Did the same with metal chlorides or metal sulfides. And that extra pair correlation that we see really only corresponds to a metal-sulfur bond. And it looks a lot like this form. So we're seeing the formation of this amorphous iron sulfide at room temperature. So I can go back to our reaction coordinate diagram and see that this low barrier is leading us to this amorphous phase, which then can crystallize into iron pyrite. So in some ways, this actually isn't new chemistry. This has been observed in thin films. So if you take a thick, thin film, so think microns, of iron and silicon and heat it to 825 degrees Celsius for a few hours, what you'll see is this strata of different compounds. As iron and silicon react, they interdiffuse and make almost every compound on the phase diagram, including those that are actually metastable at room temperature or at 825 degrees Celsius. If you're Dave Johnson at Oregon, you can actually lay down ultra-thin films using molecular beam epitaxy. So think kind of subunit cell thickness layers of, in this case, iron and silicon, which he calls atomic lasagna. You can heat that up to about 100 degrees Celsius and generate this amorphous intermediate, which loses all evidence of this strata. You heat it a little hotter, and it forms a crystalline product. So these ultra-thin films can actually lead to metastable intermediates and metastable products. And so we're seeing something very similar, but on the bulk scale now. Now we're dealing with kind of grams of powder as opposed to maybe an overall layer thickness of 100 nanometers. But it's pretty amazing to me that we can think about these two different types of pathways. So what can we do with that? We can think about making metastable materials. And so here's our perspective. We're trying to think about kinetic control where we're decreasing one barrier for a selective step. Can we do this with small molecules? And this is really the area of catalysis. Organic chemists will take organic reactants, they'll add a metal center, which can catalyze a transformation of the organic product reactants to organic products. We're kind of flipping it. We're starting with solid inorganic reactants. Can we add small molecules to have them transform selectively to a different solid-state product? So we've shown this example with water changing a pathway. Can we use water or maybe other molecules like triphenylphosphine? And so I'll show you some results on a similar type of reaction, but with copper and selenium rather than iron and sulfur. So if you take copper chloride and sodium selenide, heat them at 300 degrees Celsius for 24 hours, you get this polymorph of CuSe2, marcasite. Happens to be a superconductor. Its transition temperature is at a whopping 0.7 Kelvin. It is stable under ambient conditions. You can make it very easily by heating copper and 2 parts selenium in some sort of sealed ampule. It appears on the phase diagram. And it's basically this diffusion-controlled, thermodynamic-controlled synthesis. If you water expose this metathesis reaction and heat it to 100 degrees Celsius for 24 hours, you end up with this polymorph of CuSe2 in the pyrite crystal structure. This is also a superconductor. Its transition temperature has jumped 3 times to 2.4 Kelvin. This compound is metastable. It was originally discovered using the same apparatus that was developed to make synthetic diamond, a tetrahedral anvil press. And so think 65,000 atmospheres of pressure, 1,000 degrees Celsius. It can also be made solvothermally as nanoparticles. But here we're using very mild conditions. 100 degrees Celsius, not 1,000 degrees Celsius, no pressure. We've also shown that you can add a small fraction of this small molecule, triphenylphosphine. So what is triphenylphosphine, and how is it similar to a water? Well, they can both act as bases. Water, I teach when I teach undergraduates, water can act as either a Bronsted-Lowry acid or base, or it can donate a proton or accept a proton. Triphenylphosphine can't do that, but it can act as a Lewis base. And so here is one particular molecular representation of triphenylphosphine. It's not showing you the nice little lone pair hanging onto the phosphorus. But if we take 0.1 molar equivalents of some sort of molecule, when we use triphenylphosphine or the orthyl toluol substituted variant of that, we end up forming this metastable polymorph. But if you take molecular analogs that happen to be less basic, things like triphenylamine, which is actually a flat molecule, you don't see evidence of that lone pair, we don't get any selectivity. We get both polymorphs forming. If you take the triphenyl methyl or the tetraphenyl methyl variants, also either no selectivity or no reaction. As an absurd control, we took wax, just a long chain hydrocarbon. It doesn't really do anything. And then we took this orthomethoxy variant of triphenylphosphine, which is not molten under these reaction conditions. So we do these reactions at 150 degrees Celsius. This melts at 200 degrees Celsius. And we see perfect selectivity of the polymorph. But the reaction's not done yet. We still see some reactants. So it's slow, it's incomplete, and it suggests that having some molten phase is actually important, but it's not everything. So here we're showing small molecules can influence solid-state reactions with selectivity. We do know that the material that we make is not impurity stabilized. It's clean. We measured all the superconductivity properties. We see nearly perfect bulk exclusion of a magnetic field. We see a jump in specific heat, admittedly not the prettiest one. We can map out the superconducting phase diagram. It all looks pretty good. So how does this happen? So we can use in situ crystallography, again, showing effectively reactants going to products. But this looks a little different. In this case, we actually see 2 crystalline things forming just at room temperature, CuSe and selenium, along with the sodium chloride. These then form pyrite, and then the pyrite transforms into what we expect to be thermodynamically stable polymorph, marcasite. So let's take a look at what this looks like from a crystal structure perspective. So here's CuSe. It has this rather elegant crystal structure where you have copper in different coordination geometries, selenium in different valencies and coordination geometries. Then you have this nice simple crystal structure of copper selenide. It's cubic. You have all octahedra, these nice selenium dimers. Marcasite's pretty similar to pyrite in that you have all octahedral copper and these selenium dimers, but they're ordered in a slightly different fashion. When I first looked at these, I wondered, how is this turning into that? And then how is that turning into that? But we found a relationship. So if we just look at the copper sublattice, and these are actually in the exact same orientation I showed you before, and we've drawn these rectangles as kind of fiducial marks to help guide the eye. You can also look at the coppers forming a hexagon, but those hexagons all stay in the same place. Coppers basically don't move. You can look at the selenium sublattice, highlighted in pink. So we have these dimers and then lone selenium atoms. If you imagine some selenium interdiffusing into these layers, you additionally form these dimers, which all kind of tilt. And then to get into this marcasite phase, you have to undergo this cooperative reorganization and tilting of all these little dimers. So there's this pseudo-topochemistry that's happening. So I've shown you I can make one metastable form of copper selenate. If we put this on a map of all metastable compounds calculated from the inorganic crystal structure database, it's pretty weak. It's about 1 millielectron volt per atom above the ground state. It's barely metastable. Now, if we look at oxides and nitrides, those can get quite metastable. And so can we still use low temperature chemistry to access these stronger bonded functional materials? And there are a lot of ways about thinking about turning down the heat to access metastable oxides, whether or not you really use topochemistry, which is prescriptive. You can often predict what material you're going to get out at the end, whether or not it's thinking about lithium cobalt oxide and pulling out the lithium to get a lithium poor cobalt oxide. I'm using that effectively right now in my laptop. Or we can think about ripping out oxygen. So there's some nice work from Hiroshi Kageyama, taking actually an oxygen-deficient strontium iron oxide, reacting that with calcium hydride to make these strontium FeO2 compounds, which are these nearly perfect 2D sheets of iron and oxygen. But then we can also kinetically trap materials, whether or not it's with pressure or dielectric control, like is used industrially to make cassette tapes, chromium dioxide, or thinking about specific surface area stabilized polymorphs of TiO2. So maybe metathesis can also play a role here. But we had to think about it. But where do we look? So this is the forever problem. If you're trying to study synthesis, well, what should you study the synthesis of? And I really want to understand pathways and mechanisms. So I want to see where the pathway and the mechanism can actually make a difference. So I like to look near phase boundaries, where kinetic factors can actually play a large role. So if you look at different structure maps in various families of materials, let's take AbO3 oxides. You could look at this phase boundary, predicted phase boundary between ilmenite or perovskite phases. Or you could take an example like yttrium manganese oxide, which is right on the cusp of having the more stable, sorry, this is negative delta G, so more stable hexagonal phase over this orthorhombic perovskite, which is just tuned based on the ionic radii. So I think that's going to be a cool place to look. So if we take the yttrium manganese oxide phase equilibria and look at all the different phases that exist, so here is a phase diagram from 2006 where you have yttrium poor, yttrium rich. Below about 850 degrees Celsius, it says there are no ternaries other than a little bit of YMN205 of this brown millerite phase kind of creeping in. If we look off of that phase map, we can actually see that yttrium and manganese form a pyrochlor phase under 30,000 atmospheres of pressure, 1,000 degrees Celsius, or under fairly gnarly hydrothermal conditions, which involved perchloric acid. And this is a ferromagnetic insulator at 20 Kelvin. The perovskite phase has been made a couple different ways. First with 35,000 atmospheres of pressure, 1,000 degrees Celsius. It can also be made just from a decomposition of citrate precursors at 800 degrees Celsius. And this is a magnetically driven ferroelectric. So these don't appear on this phase diagram, and this phase diagram said there's no phases below 850 or so degrees Celsius that are stable. And so going into our metathesis literature, we get higher temperatures and get access to ternaries. So if I think about reacting zirconium chloride and sodium oxide to make zirconia, this reaction is also self-heating to 1,300 degrees Celsius. But if you gently heat it rather than rapidly heating it, you can actually stabilize some of the metastable forms of zirconia, which normally don't undergo their phase transition until above 2,000 degrees Celsius. But typically, binary metathesis reactions provide little control over ternary compositions. They like to phase separate. So there's a lot of nice examples making this ternary system between gallium, phosphorus, and arsenic, typically phase separates into gallium arsenide and gallium phosphate. But assisted metathesis reactions are a wonderful way to make macroporous monoliths of solids. So you can take this kind of complicated reaction where you have some manganese sulfate, react it with potassium carbonate and lanthanum oxide to make lanthanum manganese oxide, and you're making this salt as a byproduct. And then you're also gaining some driving force from entropy by making gaseous water and CO2. So that can somehow pull the reaction along. But you have to heat it up to about 950 degrees Celsius. But then there's this other nice approach of thinking about the precursors carefully. So if you took lithium manganese oxide and lanthanum oxychloride, well, the only way that these can react is if you keep the lanthanum and manganese together. And so that leads to lanthanum manganese oxide to make lithium chloride. This reacts at about 810 degrees Celsius. But is that a requirement? And how does that take place? So that's where we've started from. And so I was really puzzled about this assisted metathesis reaction where you're taking three different precursors to make this one ternary. And so there are a lot of different questions we can ask. We can ask, well, what's the influence of the alkali? So here we have these alkali carbonates. Well, this is a nice way about thinking about tuning the thermodynamics of the reaction. So if I consider the delta of the delta H of reaction, I'm going from lithium to sodium to potassium, the reactions actually become more exothermic. There's the other idea of specific surface area. So in these materials, or in these reactions, you start with a bunch of different particles, then you make other particles. The black would be the thing that we want. These grayed out ones would be something like the alkali halide, which can then be washed away to make a porous monolith. Does having this specific surface area help or hinder the reaction some way? But more importantly, just how does this complex three-phase reaction increase the control over composition? Or does it? And how does it do that, if it does it? So we started simply, just what's the influence of the alkali? We found a lot of surprising results. So we're going to take our time through this slide because it's way too busy. The long story short is these spectating ions, the alkalis, influence the phase selectivity. So depending on what alkali we use, we get different forms of yttrium, manganese, and oxygen. So if we use potassium, we predominantly see this hexagonal polymorph, the more stable one that's been reported. And that's only if we heat it above 850 degrees Celsius. If we keep the reaction a little bit colder, it goes to completion in terms of its stoichiometric mixtures, but we get no selectivity over one phase or another. We actually see a bunch of different yttrium manganese oxide phases all coexisting. When we use sodium, we get pure phase pyrochloro, Y2Mn2O7. This happens at 650 degrees Celsius. Now this contrasts the previous synthetic conditions of 3,000 atmospheres, 1,000 degrees Celsius, or 3,000 atmosphere, 500 degrees Celsius hydrothermal reactions. If we go to lithium, we get the orthorhombic perovskite YMNO3. And just to make it clear, we didn't actually use yttrium chloride anhydrous. We did use the hydrate, a small detail I can go into later if you're curious. But this contrasts previous synthetic conditions of high pressure, high temperature, or this citrate decomposition, which actually looks fairly similar in a lot of ways, because this is also going to evolve a bunch of CO2. So different alkalis give us different products, even though they're not showing up in the final products. To me, that says it's influencing something about how that reaction is going to completion. So I'll take a brief walk through each of them. So lithium carbonate, it's competent for making this perovskite yttrium manganese oxide, which was previously described as being metastable. As low as 550 degrees Celsius, that perovskite starts to form. So this reaction is competent for turning down the heat and allowing the reaction to take place. And we only see the hexagonal form above 850 degrees Celsius under these conditions. The phase is a little bit non-stoichiometric, so you can effectively think about it as being cation deficient. There are likely cation vacancies. We can see this from neutron diffraction or also magnetization when we try to count the spins that we would expect. There needs to be some manganese 4+ in there. And really what we're seeing is that this orthorhombic perovskite phase is actually the stable phase. That phase diagram just didn't use the right precursors to get to where the system wants to get to. The barrier is too high to make these materials at below 850 degrees Celsius. So if we do a 30-day reaction under vacuum, where we take the material we've made and just heat it up at 850 degrees Celsius, it stays that material. It doesn't convert into anything else, which is what I would expect it to do if it were metastable. But if you change the atmosphere, so if you do this in oxygen, nothing changes, but if you heat it under argon, which is slightly reducing, it should give off some oxygen, and it effectively does this and converts into some of this hexagonal phase. We've done some other controls, like flowing oxygen for 7 days. We're adding some lithium chloride flux, and the orthorhombic perovskite is still stable. So to summarize these 5 diffraction patterns, this perovskite phase is actually stable at low temperatures. It's just we've never used precursors that are competent to get there and properly equilibrated them. The stability does likely depend on the oxidizing atmosphere, but we have some new unpublished data that suggests that even the stoichiometric compound is actually still stable. Okay, on to sodium to make the pyrochlor. It's stoichiometric. We can do the magnetization, we can do neutron diffraction. Everything checks out to be a nice pyrochlor. It's not deficient on the kind of O' site if you're a pyrochlor connoisseur. And this is metastable. If we cook it for too long, if we go to 48 hours, it falls apart. It goes into some binaries and the brown Mellerite phase YMNO5. This is kind of classical metastability. Right? It doesn't stay around under the same reaction conditions. If we go too hot, it also falls apart. With potassium, we don't get selectivity. Depending on which temperature or precursor we use, we get a mixture of phases. So somehow that selectivity is gone. And just to convince you, if you just take manganese oxide and yttrium oxide, heat them up to 650 degrees Celsius, there is no reaction. You get out precursors. If you go to 850 degrees Celsius, you get a little bit of reaction, but not very much. So it's really thinking about these precursors as being much more reactive. So to just give you a quick summary of what we've found in this one little story, is we're really starting to appreciate this idea of kinetic competence. We need precursors that are actually reactive at lower temperatures. It can resolve low temperature equilibria and new synthetic dimensions. So we found maybe this phase diagram needs a new phase there. But we can also think about taking this phase diagram and pulling it off into a completely different axis, whether or not it's the alkali species that's probably tuning some sort of thermodynamic variable that is consistent with our synthetic observations, but we don't know what that is yet. Is it specific surface area? Is it a local strain potential? I don't know. And so what we're hoping to build up over the few years is a predictive understanding of reaction pathways. I want to know why lithium does this, so maybe I can pick that for a different reaction. If I think about the field of organic chemistry to make our beautifully ornate stereochemically controlled drug molecules, we know how to make them because we have a library of reactions to choose from. In solid-state chemistry, we don't have a library. We have a couple of techniques that are very powerful, but it's a very small number of options. And so moving forward, I'm a part of an EFRC out of this wonderful group of collaborators where we're really trying to figure out how reaction pathways take place. And so here's a quick snapshot of this exact reaction with lithium under flowing oxygen, data collected here at 17 BM. I'm making this small because it's a complete mess. It's a very complex reaction. And so we're trying to think of new ways to draw out what's happening. So here is a quantitative phase map of every phase that's in there. And we've highlighted them based upon whether or not they have lithium, manganese, or yttrium. You can see a lot of things coming in and out. And what I want you to pay attention to is when this orthorhombic phase grows in. Well, it grows in at the expense of lithium manganese oxide and these yttrium oxychloride phases. Well, that's interesting. That tells us what effectively the competent precursors are. But then how do those react? And that's really where we are with this, trying to understand, well, what are the quantitative phase relationships of all of these different precursors, following the atoms. So to conclude and provide some outlook, I think we're moving towards this idea of reaction by design. Our long-term goal is to understand how reactions take place in order to prescribe new reactions for new and metastable materials. We're finding that these metathesis reactions are wonderful to study because they're kinetically competent. They have that low initial barrier that allow the system to evolve in one pathway or another. They enable kinetic control. We've used in situ diffraction and pair distribution function analysis to identify intermediates and competent precursors, whether or not it's this amorphous iron sulfide phase or copper selenide. Different reaction pathways can often yield metastable products, as I've shown with copper selenide or some of these yttrium manganese oxide phases. And we're just scratching the surface of understanding how small molecules can have selective reactivity for solid-state reactions. That's catalysis. We've written this up as a perspective. Be happy for you to read it, and I'd love to discuss that with anybody. And lastly, I really need to thank a terrific group of people. Again, this was mostly Andy Martinolich. This work was all supported by more or less my NSF Career Award and also some of the earlier work through the W.M. Keck Foundation. We're carrying on the next generation of the work in our Next Generation Synthesis Center, or Genesis. I'm grateful to other private foundations, the Research Corporation, Alfred P. Sloan Foundation, and I really couldn't do any of this work without user facilities from the DOE, whether or not it's Argonne, whether or not it's Oak Ridge. I'm just incredibly grateful, and you've allowed me to keep my job. So thank you for your time.
Work the mic.
Very nice, very comprehensive in terms of the number of things you've looked at. But there was something I was looking for which I didn't see, and I'm wondering either you've edited it out by choosing what you work on, or it just isn't relevant in what you're doing, and that is amorphous phases. So do you have situations where you have like crystalline precursors, you go through an amorphous intermediate that's well defined and then back into a crystalline phase at the end?
So in the one case that I showed was an iron sulfur phase, where we do see that amorphous phase, but that was because we saw so much iron and sulfur was missing that we really had to look. And we think there have to be more of them. We haven't looked explicitly. When it gets to how much of the sample it is, if it's below 5 mol% of the sample, we're just not going to ever be sensitive using the techniques we're using. Where I think we're really going to start to learn is when we start looking at spatial resolution. Right? The biggest thing that I've ignored in all of this is looking at microstructure. Right? Microstructure is everything. That's going to tell us who's reacting with what, when, and how. And I think that's, when we start looking there, well, I think we're going to see a lot more evidence for highly disordered phases that we just will never see with crystallography. But yeah, part of it was selective editing, but part of it is we just haven't known to look in cases where it really matters.
Hi, that was really nice to see all those results. The last bullet here, the small molecules, it sounded like you were saying you were just getting into this, but I thought I'd give you the opportunity to say more about it. It seems very interesting that you can get such a strong effect. I don't know, how are you going to, what's the next step for figuring out what's going on there?
That's a great question. So one specific next step is to look at, for instance, what water is doing. We haven't looked carefully at that, so we actually have an experiment scheduled this run cycle to look at that in that one specific case. The other are just to make simple approximations, right? To think about, is this behaving as a Lewis base? So for example, if I take triphenylphosphine and try that on the sulfur-based systems, it actually doesn't work. The bond between sulfur and triphenylphosphine is effectively irreversible, so it pulls away the equilibrium. It doesn't work the way that we want it to. We do have some other approaches on thinking about kind of how to activate other molecules. A great place to start is just things that act as good ligands. to metals. So if I think about making coordination complexes, or kind of iron palladium complexes that are used industrially, they have things like phosphine-based ligands or nitrogen-based ligands. So those could be a good place to start. But the challenge is we don't want things to be solvating. I think once you move to things that look more like solvents, they never let go of the metal or the anion. We have a couple of tricks up our sleeve. We have found one molecule that seems to be good at reducing the temperature for making iron sulfur that's not water, but we don't understand how it's working or what it's doing. But hopefully we'll be able to share those results soon.
So I have a question, really nice talk. I have a question concerning the size of the crystals during growth, concerning landscape. For example, for some of these magnites, you mentioned many different possible polymorphs. One of the questions is, say, concerning, say, the 113, the pseudo-cube magnites. It seems some of these compounds simply couldn't grow large enough, for example.
Right.
Does this have to do with the competition of polymorphs, or is there any way you could think of to identify the path that concerns the energy on a larger length scale?
Right, so I think for this particular example, at lower temperatures, they're certainly less crystalline, but they are reasonably crystalline. I don't know exactly, actually I do know the size dimensions. I think I put that in here. Yeah, there we go. So if you just look with scanning electron microscopy on that perovskite phase, we're getting kind of to, this is the washed material, kind of about micron particle sizes. Whether or not that's the actual grain size, we haven't looked, but they're getting to be reasonably largish for relatively low temperatures. Granted, this was at probably the 850 degrees Celsius reaction. The pyrochlor has these tiny little particles that are definitely less than a micron, but very sharp Bragg peaks. So there's absolutely some size dependence. One thing I didn't talk about at all today out of time is in the perovskite, there's a large amount of lattice strain due to the non-stoichiometry, so that's also contributing to some of the peak broadening. But again, microstructure is something that we have completely avoided looking at because it increases the complexity of the problem by immensely. And that's actually, looking forward, one of my main interests in trying to understand.
My question is on iron sulfide system. Phase diagram you showed had a couple of intermediate phases, but there are more than that in the iron sulfide diagram. So are you at a point where you can actually dial and say, I'm going to synthesize Fe3S2 100%?
We're not at that point yet. I'd love to be there. We actually do see Fe3S4, which is metastable under normal conditions as one of the intermediates, but we haven't figured out how to stop it there. We basically just need to keep looking and maybe dial the reaction as it's happening. But I need a synchrotron to do that, right? I can't do this at home because it's only there for a short point in time and temperature.
So high pressure didn't show prominently in your...
We have avoided the pressure.
That's another way to dial it.
Absolutely. I mean, this is just one set of, I mean, most of these are just linear heated temperature. I mean, you could even play with temperature profiles. The phase space is huge, but absolutely pressure would be a really interesting variable to apply and see if things are behaving the way that we would expect them to do.
I have to raise this question. How do you see the influence or the potential for machine learning to help you to predict the kinetic reactions? Is it something you're already pursuing? And I know you have a proposal, but also what do you need from us to be successful in this machine learning?
So right now our bottleneck is interpretation of these color maps, right? So that's a wonderful opportunity for automatic phase indexing. I've personally tried this myself. If you take things like principal component analyses or other types of matrix factorization problems, just SciPy, you can get access to all of them. They don't work very well for diffraction because of thermal expansion. And not every phase is a nice cubic crystal structure that expands isotropically. Right? You can have Bragg peaks moving left or right depending on what type of crystal structure it is. my approaches as a non-data scientist haven't worked, but we're starting to collaborate with experts in data science to figure out, is there a better kernel to solving these problems? And that, to me, is one of the things that I'm most interested in from collaborators, is to figure out how do we go from a 3-month data interpretation problem into 3 hours. So that would be very valuable. That, and then also imaging, right? Trying to figure out which atoms are going where at what time. But then we also have a data problem. So I think we need to solve the simpler problem of phase ID, which is still very hard. But I'd love to get like a probability of having a certain phase in a particular mixture. Rather, I don't need an absolute certainty.
Any other questions? I'll just thank Jamie again.